Hey guys, today we're going to go over some notes on inverse matrices. So the definition of an inverse matrix, or the identity matrix in this case, is E1, E2, E3, etc. And with this, it is having 1 with the columns and every other note being 0, every other position. So we can have it also written like this. I by n by n matrix, with each row being I and each column being j. If I is equal to j, then it is 1, else everywhere else it's 0. So we know that a times I is always equal to I times a, which is equal to a. Since we think about this mathematically, if we are multiplying only the single row or column from each row or column, there's a linear combination of the column itself and 0 of the other columns. And because of that, you get the matrix itself. Doing it the same way, switching it does not make a difference, simply because, again, you are doing the columns of A in that case, which will still be in the right places when multiplied with the matrix I. An inverse matrix now is A turning into A inverse. And we do this when A times A inverse equals I. So the inverse times the original matrix itself should always equal the identity matrix. So for a non-singular matrix A, we say that A negative 1, or A inverse, is the unique matrix such that if AX equals B, then X inverse X is equal to A inverse B. So we are looking specifically at non-singular matrices. This means that there is only one solution, and thus there does not exist a inverse. But we'll go over that a little later. Non-singular means that the rank is full and the columns are linearly independent. Doing this way, we get the same proof. Now, the main thing over here that you probably see is, what do you mean for a non-singular matrix A? Well, many matrices don't actually have inverses. I'm pretty sure this is wrong, but I'm going to double check. But yeah, I think do your own research on this and call it a day. See you guys.